All right, let's dive into electromagnetic induction. We've got some physics textbook excerpts here, going to get into the work of Faraday, Henry, and Lenz.
Oh, this could be good.
Some people might hear physics and think, uh-oh, here we go.
Yeah, I get that.
But this is where physics gets really cool, and it's way more connected to our lives than you might think.
Absolutely is the foundation of so much of our modern technology.
Right, we're talking about how changing magnetic fields can actually create electric currents.
Generating electricity from magnetism. It sounds almost magical, but it's the basis of how we power our world.
Exactly. Everything from our homes and devices to wireless data transmission, it all comes back to electromagnetic induction.
Imagine a world without it.
No thanks. No smartphones, no internet, not even electric lights.
It'd be a completely different world.
So let's rewind back to the 1830s. We've got these pioneers, Faraday and Henry, doing these groundbreaking experiments.
Oh yeah, with just coils of wire, magnets, and a galvanometer.
A what?
A galvanometer, it's a device that measures electric current.
Got it. So they're messing around with these simple tools, and what do they discover?
Something truly revolutionary. They found that just by moving a magnet near a coil of wire, they could induce an electric current in the coil.
Wait, so just waving a magnet around can create electricity?
That's the basic idea. Think about it. You could wave a magnet over your phone, and boom, it starts charging.
Okay, maybe not quite that simple.
Haha, right. There's a bit more to it.
But that's the power of induction. So how does it actually work?
Well, to really understand it, you need to wrap your head around the concept of magnetic flux.
Magnetic flux. Sounds intense.
It's not as complicated as it sounds. Think of it as an invisible flow of magnetic force through a surface.
Okay, I can kind of picture it.
And when you move a magnet or a coil, you're changing this magnetic flux, and that's what generates the electric current.
Oh, I see. So it's like disrupting the magnetic flow that sparks the electrical energy.
That's a great way to put it, and that's where Faraday's law comes in.
Right, Faraday's law, that's the one that explains the relationship between changing magnetic flux and the strength of the induced current, right?
You got it. The faster the magnetic flux changes, the stronger the induced electromotive force, or EMF.
EMF, that's what drives the current.
Exactly. It's a direct relationship, more change, more power.
Yeah, there's a great story about Faraday. When someone asked him about the practical use of his discovery, he said, "What's the use of a newborn baby?"
What a response. Little did he know that induction would grow up to power the entire world.
It's incredible to think about. So Faraday's law tells us how strong this induced force is, but what about its direction?
That's where Lenz's law steps in. It basically says that nature doesn't like change and tries to resist it.
Resist it? Like how?
The induced current will always flow in a direction that opposes the change in magnetic flux.
So it's like nature is pushing back, trying to maintain balance.
Precisely. And this pushback is really important because it ensures that energy is conserved. You can't get free energy from induction.
Oh, I get it. So you have to put in effort to overcome this opposition.
Exactly, just like in any other physical system. Now here's where things get even more interesting. Induction isn't just about magnets and coils.
What do you mean?
It's a more general phenomenon. Even a simple metal rod moving through a magnetic field can experience it.
Wait, really? Just moving a piece of metal?
Yep. It's called motional electromotive force. The charges inside the rod experience a force as they move through the field, and this creates an induced EMF.
So it's like the motion itself, combined with the magnetic field, is what's generating the electrical energy.
You got it. And this highlights the fundamental nature of electromagnetic induction.
Okay, that's super cool. So we've got magnets and coils, moving metal rods, and now you're going to tell me there's another layer to this.
There is. Let me introduce you to inductance. Think of it like electrical inertia.
Inertia, that's the tendency of an object to resist changes in motion, right?
Exactly. And inductance is a measure of how much a circuit resists changes in current.
So a circuit with high inductance is like a heavy object, hard to get it moving.
You got it. It's like a built-in resistance to sudden changes in the flow of electricity.
That's fascinating. So are there different types of inductance?
There are. There's mutual inductance, where two nearby coils affect each other.
Like they're interfering with each other's magnetic fields.
Exactly. And then there's self-inductance, where a coil induces an EMF within itself because of its own changing current.
Whoa, so a coil can actually impact itself with its own current.
It's kind of like a self-fulfilling prophecy in the world of electromagnetism.
That is wild. So what do we actually do with these inductors?
They're essential components in all sorts of electronics. They're used for filtering signals, tuning circuits, and even storing energy.
So they're like tiny electrical traffic controllers managing the flow of current.
That's a great analogy, and it's amazing how these abstract concepts translate into real-world technology.
Right, it's like we're peeling back the layers of the universe and seeing how everything is connected.
Exactly. And speaking of real-world applications, let's talk about the AC generator. That's a prime example of how we harness electromagnetic induction to power our world.
All right, let's hear it. The AC generator, how does that work?
Well, it's all about rotating a coil within a magnetic field to generate alternating current, or AC, the kind of electricity we use every day.
So it's like a continuous dance between magnets and coils, creating this flow of electricity.
Precisely. And the beauty of it is that the basic principle remains the same, whether you're talking about simple demonstration or a massive power plant.
It's incredible how something so fundamental can be scaled up to power entire cities.
It all comes back to that magical phenomenon we've been talking about, electromagnetic induction.
Mind-blowing. But before we get too ahead of ourselves, let's take a step back for a second. We've been talking about how moving magnets and coils create these electrical currents, but I've got a question.
Shoot.
Is the relationship kind of a two-way street? Could changing electric fields maybe create magnetic fields?
Ooh, great question. And the answer is yes. It's this incredible symmetry at the heart of electromagnetism.
So it's like a two-way street.
Exactly. And realizing this led to a huge leap forward in our understanding.
We went from thinking electricity and magnetism were separate to realizing they're all part of the same force.
One elegant framework.
So who made this connection? Was it Faraday again?
This time it was James Clerk Maxwell, a brilliant Scottish physicist back in the 1860s.
Maxwell. Okay, yeah, that name rings a bell.
He took all of Faraday's experimental work and created a set of mathematical equations to describe it.
Maxwell's equations, man, those bring back some memories. Mostly of me being completely lost in physics class.
They can be a bit intimidating.
But they're basically like the rule book for how electric and magnetic fields interact, right?
That's a great way to put it. And they predicted something amazing. Electromagnetic waves.
Hold on, so we've got these changing magnetic fields making electric fields, and then those changing electric fields making magnetic fields, and this creates waves.
Exactly. It's this incredible dance of fields generating each other as they travel through space.
And they travel at
the speed of light.
No way. So you're telling me that light itself is an electromagnetic wave?
Bingo. Light is just one small part of a whole spectrum of these waves.
So there are other kinds of electromagnetic waves besides light?
Oh yeah, ton. We've got radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays.
Wow. It's like a whole hidden world of energy we can't even see.
And it's all part of the same family, connected by this fundamental interplay between electricity and magnetism.
So cool. Okay, back to those electromagnetic waves. We've got these waves zipping around at the speed of light, but how do they actually carry energy?
It's all in the oscillating electric and magnetic fields. They act like a package, delivering energy as they travel.
So that's how we feel the warmth of the sun on our skin.
Exactly. And it's how we use radio waves to transmit information over long distances.
It all comes back to those waves, so the amount of energy they carry depends on
their frequency. Higher frequency means more energy packed into each wave.
So that's why things like X-rays and gamma rays can be so dangerous?
Right, those high-frequency waves pack a serious punch. But back to Maxwell's equations for a second.
Yeah, I'm still trying to wrap my head around those.
Think about it this way. You might not see the equations themselves written out every day, but you experience their effects constantly.
Really? Like how?
Think about rainbows. Those beautiful colors are a direct result of how light, as an electromagnetic wave, interacts with water droplets.
Wait, so rainbows are basically a demonstration of Maxwell's equations in action.
You got it. The way different wavelengths of light bend and reflect, creating that spectrum of colors, it's all described by Maxwell's equations.
That is so cool. It's like these equations are hidden all around us.
They are. Even your smartphone relies on them.
How so?
It communicates wirelessly using radio waves, right?
Right.
Well, guess what? Maxwell's equations describe exactly how those waves work.
So every text message, every call, it's all riding on these invisible waves described by these equations.
Exactly. It's mind-blowing. And even the GPS you use to navigate relies on Maxwell's equations.
How?
It uses timing signals from satellites. And those signals are transmitted via microwaves.
Which are another type of electromagnetic wave.
You got it. So those equations are essential for modern life, even if we don't see them written out every day.
It's amazing how these super complex ideas impact our everyday lives. So we've gone from moving magnets and coils to rainbows and smartphones.
That's quite a journey, and it all highlights how these fundamental principles of physics shape the world around us.
Totally. So now that we've covered all that, I've got one final question that's been bugging me.
What's that?
We've talked about how these electromagnetic waves travel through space, but can they travel through time?
Ooh, now that is a mind-bending question. And the answer takes us into the realm where electromagnetism meets Einstein's theory of relativity.
All right, so we're going full-on cosmic now. Buckle up.
Einstein's theory of special relativity revolutionized how we understand space and time.
So tell me more about this theory.
It showed us that they're not separate entities, but interwoven into a single fabric space-time.
Space-time, like they're two sides of the same coin.
Even closer, imagine it like a tapestry, with space and time as the threads, inseparable from one another.
Okay, I can kind of picture that, but how does this connect back to our electromagnetic waves and time travel?
Well, one of the key principles of special relativity is that the speed of light in a vacuum is constant for all observers.
What do you mean by that?
It means no matter how fast you're moving, even if you're traveling at a significant fraction of the speed of light, you'll always measure the speed of light as the same constant.
So even if I'm racing towards a beam of light or running away from it, I'll still perceive it as moving at the same speed. That doesn't seem possible.
It's totally counterintuitive, but that's the reality. And this seemingly simple idea has mind-blowing consequences.
Like what?
It means that time and space themselves must warp and stretch in order to keep the speed of light constant.
Okay, my brain is officially starting to hurt.
I know, it's a lot to take in. But think about this. Because electromagnetic waves travel at this cosmic speed limit, they actually experience time differently than we do.
So from our perspective here on Earth, where we're moving much slower, light from distant stars seems to be traveling through vast stretches of time.
Exactly. When we look at starlight, we're essentially looking back in time.
Whoa, it's like a cosmic time machine.
It really is. The light we see from a star that's billions of light years away has been traveling for millions of years to reach us.
So by observing this ancient light, we can study the history of the universe.
Precisely. Astronomers use this principle to peer into the past and understand how galaxies formed and evolved over billions of years.
That is just incredible. But what about traveling forward in time? Is that even something within the realm of possibility?
That's where things get even more speculative. Einstein's theory of general relativity, which deals with gravity, suggests that massive objects actually warp space-time around them.
So a really massive object like a black hole could actually warp time itself?
Theoretically, yes, the intense gravity of a black hole could create a region of space-time where time flows much slower relative to observers outside that region.
So you're saying if I could somehow survive a trip near a black hole, when I came back, everyone else would have aged much faster than me.
That's the idea. It's called time dilation, and it's one of the most mind-boggling predictions of general relativity.
So we might not be able to hop in a time machine just yet, but the way these electromagnetic waves interact with space-time allows us to glimpse into the past and even consider the possibility of time travel in the future.
It seems like the rules of the universe are a bit more flexible than we tend to think.
It's both exciting and terrifying at the same time. But before we get too carried away with time travel fantasies, let's bring it back to the main event.
Right, electromagnetic induction.
We've covered a ton of ground today, from those early experiments to mind-bending theories about space-time.
We started by looking at how moving magnets and coils create electric currents, and we ended up contemplating the nature of time itself.
It's been quite a journey, so just to recap, we've learned that changing magnetic fields create electric fields, and vice versa.
This creates these incredible electromagnetic waves that travel at the speed of light.
And these waves underpin everything from the way we generate electricity to the wireless technologies that connect our world.
And Maxwell's equations beautifully describe this dance of electricity and magnetism, predicting phenomena we experience every day.
So much to think about. This deep dive has been truly electrifying.
I'm glad you enjoyed it. It's always fun to explore the wonders of science.
Absolutely. And it's a good reminder that there's always more to learn, more to discover.
So keep asking those questions, keep exploring, and never stop being curious about the world around us.
Great advice. Thanks for joining us on this electromagnetic adventure. Until next time, keep those brainwaves buzzing.
See you next time.
All right, so we're picking up where we left off, back in the realm of space-time and relativity.
It's the way things get really interesting, I think.
We're tackling the big question, right? Can electromagnetic waves travel through time?
A question that pushes the boundaries of what we know.
Blending electromagnetism and Einstein, that's a potent mix.
It is. Einstein's theory of special relativity, that's our starting point.
Special relativity, okay. It's all about how space and time are connected, right?
More than connected, they're interwoven into this single fabric we call space-time.
So not just separate things like we usually think of them.
Right. Think of it like, a tapestry.
Okay, with space and time being the threads.
Exactly. You can't have one without the other. They make up the whole thing.
That's pretty wild to think about, but how does this tie into electromagnetic waves and time travel?
Well, special relativity has this key idea. The speed of light in a vacuum, it's constant.
Constant, you mean no matter what?
No matter what. It's always the same speed, even if you're moving towards the light source or away from it.
Hold on, so even if I'm like flying in a spaceship at super speed towards a beam of light, I'll still measure its speed as the same as if I was standing still.
Yep. That's the mind-blowing part.
What? How is that even possible?
It seems counterintuitive, but that's the reality we observe. And because of this, to keep that speed of light constant, time and space themselves have to adjust.
Adjust, like they change.
They warp, they stretch, they do what they need to do. which is a pretty crazy concept.
Okay, yeah, my brain's definitely hurting a little now. So how does this connect to electromagnetic waves traveling through time?
Well, since those waves, including light, travel at this ultimate speed limit, they experience time differently than we do.
Differently, you mean time moves slower for them?
Not exactly slower, but from our perspective here on Earth, bound by our own slower experience of time, light from distant stars, well, it seems to have been traveling for incredibly long periods.
So when we look at those stars, we're seeing them as they were millions of years ago.
You got it. That starlight has been traveling across vast distances, and to us, that translates to looking back in time.
That's insane. It's like a real-life time machine just by looking up at the night sky.
In a sense, it is, and astronomers, they use this all the time by studying the light from distant galaxies billions of years old. They're literally piecing together the history of the universe.
Wow, that's just incredible. But what about going the other way, traveling forward in time? Is that something science even considers?
Now, that's where we get into more speculative territory. Einstein's theory of general relativity, which deals with gravity, suggests that massive objects can warp space-time around them.
Warp it, like bend it out of shape.
Exactly. Think it's a bowling ball on a trampoline, how it makes a dip.
Yeah, I can picture that.
Well, massive objects do something similar to space-time. And the more massive the object, the greater the warping.
So a really massive object, like a black hole.
Ah, yes. Black holes are like the ultimate space-time warpers. Their gravity is so strong that they create these regions where time flows much slower compared to outside.
Okay, let me get this straight. You're saying if I could somehow survive a trip near a black hole, when I came back to Earth, everyone else would have aged way more than me.
That's the basic idea. It's called time dilation, one of the trippiest consequences of general relativity.
So while we might not be able to build a time machine just yet, the way electromagnetic waves interact with space-time, it's pretty mind-blowing.
It is. It lets us see into the past, and it even opens up these theoretical possibilities for time travel in the future.
It's like the universe is full of these hidden pathways and possibilities. We just need to figure out how to navigate them.
Exactly. There's so much we still don't know, so much left to explore.
Well, I think it's safe to say this deep dive has been a wild ride. We started with simple magnets and coils, and we've ended up contemplating time travel and the nature of reality itself.
It just goes to show that even the most basic principles of physics can lead to some incredibly profound and mind-bending concepts.
It's been a real journey. And a great reminder to keep asking questions, keep exploring, and never stop being curious about the world around us.
Couldn't agree more. It's been a pleasure diving into this with you.
Likewise. Thanks to everyone for joining us on this electromagnetic adventure. Until next time, keep those brainwaves buzzing.
And keep exploring the universe.